Hello folks, welcome to my channel. This is Cap, and today I'm going to talk about the data analysis in cosmology. Although I have made few videos on data analysis in cosmology and you people have liked it so much, but this video is going to be a little bit different where I am going to talk about the radiation and all this stuff you are going to see. So the outline of the video would be very simple that I'm going to first start with the basics of cosmology, basics of LambdaCDM, where I'm going to introduce how we are starting actually from the action, and then we are going to derive the necessary equations, and then we are going to see that how you can actually write your code in Python and what are the data sets we are going to use to confront our model. So basically, we are going to use the Hubble data, supernova data. Supernova data, I'm going to talk about the Pantheon, and similarly, you can use the DESI supernova data, right? And similarly, I'm going to just give you the glimpse that how you can use the DESI BAO data. Similarly, you can use the SDSS BAO data, and also I'm going to give you some hint how to do the Planck data. All the things, all the data, and all the codes you can find it in my GitHub. So you have to first go to my github.com and then /sleonardocap. This is my channel, and from there you have to go to cosmological data. So once you are hitting in this /sleonardocap, you will see bunch of things. Here you have cosmological data, MCMC. These are things which are actually in public, and dynamic system in cosmology. This mathematica I have already given here. MCMC for some other Python notebook over here, but here is my code for cosmological data analysis. Once you click on this, you have to go here. Here you can see a lot of things where you can read the README, the new updates that I am doing very frequently, where I have given you what are the papers that you have to cite if you are using my algorithm, any algorithm. And here I have already updated what are the YouTube links you can find in order to understand those particular codes. But here in this video I have updated everything, so you have to actually look to this video if you don't understand how to write your own code and how to use it. All right, so the everything is very simple, and it is made, the code has been written in such a way that anyone who has little idea on Python, or if he is in graduation, he can actually deal with it, and he can study he or she can study their own models. So once you are here, what you can do, you can just simply hit back, hit to BAO data, and from here in the BAO data, I have given many files. Here you can use the BAO lambda CDM equation where you have to apply your model, modify your model, and from there you can estimate the likelihood. Here I have already given the BAO data as this is BAO. There is for Planck data, there is for DESI BAO data, and there is the data sets. For few data sets I have uploaded, and there are some, if you want to use the Planck supernova data, these data sets are very huge, so I have not given it. You have to go and download it from their GitHub repository. All right, and here is the Jupyter notebook for calculating AIC and BIC. Here is the execution file. If you want to use emcee sampler, then you can use this data file, this file, to use it. If you want to use the Polychord is very advanced. If you want to use the scalar field and all these things, then you have to use the Polychord, because Polychord uses the nested sampling. There is a slicing things, hyper slicing. So for those sampling, which is gradient based sampling, and those are very important if you have large parameter space, and there are few parameters which are kind of degenerate. Degenerate means that there are two parameters, let's say A and B. So if you just adjust B in a positive direction, then A will be adjusted in negative direction. So they are kind of degenerate. You cannot constrain it, right? So the if you use emcee, you are not going to able to constrain it, but you have to use some Polychord. This sampling, I'm going to talk about this one. Then you can easily get the constraint on A and B, right? So what you have to do, you have to again go back first, and let's see, where is it? Let's say this is my cosmological data, and you can easily download it from here. You have to go to code and download the chip. So once you are downloaded, it will be automatically downloaded to your wherever the downloaded path you have given, and once it is downloaded, you will be located to this folder. You have to unzip it. Once you are unzip it, you can go to the BAO data section, and where you can see all the files. So here I have the files, that is this figure which I have already run it, and I have given that, let's say if you have LambdaCDM and you are running it in emcee, you are not going to get a good constraint. I'm going to explain why. But if you are using the LCDM Polychord, let's say that you are using this LambdaCDM and it is running, it has been run in Polychord, and I have used this compressed Planck data, then this is the kind of image or the contour plot you will get. Here omega lambda is the dark energy component, which is 68%, as not is 67.51, which is you can get the same kind of value from 2018 Planck data. And this is the baryon density, because once you are doing the Planck, you know that you can get the baryon density constraint on the baryon density, right? So this is omega b0, which is the baryon density. H square is h0 over 100, right? So this is the constraint you will get. So this is the framework that I have built, which is very close to if you see the Planck data paper. So that's why I have updated the code in such a way that you will get a feeling that, oh, this is the same thing we are doing, right? And similarly, you can see the status, how we can get the AIC, BIC, and all this stuff. There are screenshots I have shared. Okay. So how are we going to start? Well, I cannot edit the code here. So what we have to do, you have to just, if you are using the Windows, then you have to open the VS Code. How you can open the VS Code? So you can follow your description, how to open your VS Code, how to import this folder. In the Windows, it's very easy. I can just simply shift and press my right click, open the terminal. Once I'm inside the terminal, I will write code, and this is dot. So once I have done it, then my VS Code will automatically open, and it will import all the files, necessary files. It means that if you see the path of this VS Code, it will simply show you that I am inside that folder. All right. So that is why you can simply that is how you can launch your VS Code directly on your desired folder. Okay. Now the LambdaCDM framework has been updated here. If you go to BAO LambdaCDM equation, here you can see everything. Now this is the preamble. You have to keep it in the way that it is. If you are new to Python, like this is the importing the standard libraries. All right, I have already installed Python, so if you want to know how to install the Python, you can see some other videos, or I have made the video. You can just just go and check it out. All right, so import, these are the, you can say that some libraries we have to import, just like you can do in your latex. You have to install some kind of packages. So this is the similar thing. So the way you are importing the packages in your latex, the similar thing we are doing here with the Python, right? So this is the SciencePy library, which is a very standard one, NumPy library, that is handling with the arrays, which is very important and very, very amazing, because now we are doing the data analysis. So NumPy library becoming is the important one. SciencePy is important one, because we have to do a lot of differentiations, a lot of integration. So we have to do a lot of all these computations, all this can be handled by SciencePy, right? So these are my folders. If you are making some folder, for instance, I have made BAOPy, I have made the compressed Planck pi. So for likelihood or for the data, I have made different folders for files. Now these files are actually inside this particular folder. Right now, if I have to import, because I don't want to write every piece of my code in a one thing, right? That's why I have made a few different files. And how can I integrate everything? I can simply import it. Import BAO. Now here you can import a file which is ending with .py. That is what you can import, right? So you can see, if you just click control and BAO, directly click it, you can directly open the bao.py. Here I have given all the data sets, all the errors, and from here I have given how you can calculate the likelihood for it. All right. So similarly, if I have the new DESI BAO, this is the new DESI BAO data, data from the dark energy survey uh, uh, survey from the galaxies. Here you have to use the DESI mean. So this data comes with the covariance matrix. So I have imported all these covariance matrices, and then here is the code to calculate the DESI BAO. Once you have written everything, you don't have to do anything. You have to just do few things, and automatically the code will handle everything for you. You don't have to do anything. So if you don't understand these advanced thing, you don't have to worry about it. You will later understand. You can maybe use some help with ChatGPT to understand what are these. I'm not going to do everything in detail. Maybe in later video I will define all the technicalities related to Python, but here I'm going to first explain that how you can build your own model and study. All right, so this is how I have used the compressed Planck. Just control and click. Here I have given you, again I'm importing the libraries. I have given the link, the article that you have to follow, where you can find the data, and there I have already generated the inverse of covariance matrices. All right, so again this data is much more elaborated than previous data set I have used, and this data set is very efficient to handle models beyond LambdaCDM. So if you have a model like LambdaCDM, for instance, you use CPL model, and you don't want to use any interaction between dark matter and dark energy, then this data is obviously good, but you can use the 3 parameter data. All right. But here this data is much more important if you are using, let's say, if you want to find out the extra relativistic species in our universe. For instance, the early universe neutrinos. So you can use the data to actually constrain on the relativistic parameter that is called N effective. Or maybe you want to test your dark energy dark matter interaction, then you can use this data. Or maybe your FR gravity theories, you can use this data. All right. So here I have used the class, and inside the class I have made the definition package, and you don't have to do anything. You just have to import it and done. So once you are using my code, you don't have to do anything. But understanding is much more important. What I have done, how I am doing it, that is the much important thing. That's why I'm making this video, because so many people, they do data analysis, but they don't understand anything about data analysis, what they are doing. There are a lot of different packages you can see. There is something called Cobaya, there is Monty Python, and so on. These have been made in a very complicated way. They are the very professional computer scientists, they have made it, right? So here I'm not a computer scientist, I'm a physicist, and from my point of view I have to make it in a classroom way, so that you can make your own software to do your data analysis section, right? So you can teach that, oh, this is the way we have to do it, this is the observable, this is how we have the model, and this is I'm going to get different things, right? So that is why I built my own code, and I have optimized it. The best thing about my code is that there is not several pieces, there are not million pieces. All the things you can see that, okay, this is the way these are things coming out, and this is how I have used these pieces, and I am getting the result. That's it. So that is the significance of this code, that this code is much simpler and can do a very amazing job. And even if in your laptop with not many cores, like you don't have to use the 100 cores, 1000 cores, right? You just have to let's say that you have a very good computer and a laptop with 10 cores. Let's say you have a 6 CPU, then it will have 2 cores for each CPUs, and then it will becomes 12 core, right? Or 12 CPUs. With the 12 CPU, you can use the multiprocessing technique, and it will accelerate your code, right? So that's the amazing thing about here. You don't have to know a lot of professional thing in data analysis or in Python. You can simply start from here. All right. So here I'm importing the data. You don't have to know about it. Now I have made a definition file. So what is this definition file? It's a kind of own formula. Like, we are not using that particular thing unless we have to use it. So let's say you have your notebook, and you can make your own kind of section. Now inside that particular section you want to keep something. Now in any particular time, if you want to refer something, you can just simply come to this section, and you can simply say that, okay, you can find something in this section. So that is how you have, these are kind of piece of blocks. So when I'm using definition, I can define my piece of block, that this definition is this block is containing the equation. You have to name it first. What are the equations, and what are the parameters that is going to be useful, right? So when I'm writing my equation, then I must have some time variable, obviously, because it's my differential equation, then it is varying with time. What are the variables? Variables means that let us say you are writing dx over dt. So your x is becoming a variable. Now what are the parameters? Let's say you have a dx by dt is equal to lambda into something, let's say t, right? So your x variable is changing with time, which is going to be proportional to lambda into t. So lambda is your parameters, right? Because you don't know what is your lambda. Now based on this differential model, you have certain data and you want to find what is what is the range of that particular model, what is the range of particular lambda, particular parameter. So parameter is this one variable, you understand x, and what is how your x is varying. The x is varying with respect to t. So these are my essential building block to define the equations. All right, so I have described everything, but so now this is the important thing, that okay, what are my variables, how I am going to define it, that is what I'm going to now explain it. Okay, and here I am solving my ODE, like ordinary differential equation. How I'm going to solve it, I'm going to talk about in a bit. And once everything is happening inside ODE, because once I have defined my ODE, I have already the different block for equation. I will simply here I will solve my differential equation, and once I have solved my differential equation, I can easily get my Hubble solution. And similarly, if I got the Hubble solution, then I can construct the luminous density. Once I have luminous distance, once I know these things, I can calculate everything, right? These are the important things in order to actually get different things, right? So these are a little bit complicated code, and you don't have to worry about it. Here I'm using the likelihood estimation, that okay, I have a supernova data, then what are the things that I have to keep in mind to actually calculate the chi-square for, or chi-square for supernova data. Chi-square is how I'm going to define chi-square. We'll talk about it in a minute. That is the likelihood. Similarly, I have defined for chi-square likelihood for your Pantheon data. So this one is very important one. All right, and similarly, I have already made a different file for the BAO calculation, different file for Planck calculation. I am just importing over here, and I can use the total chi-square, because you see that if you use the supernova data, it cannot constrain your H naught. There are two supernova data. One is from the SOOS result. Now in SOOS, they are using the Cepheid variables, and they have calibrated using the Cepheid calibrations. They are computing H naught. So from the Cepheids, they actually constrain their supernova brightness. And if you know the supernova brightness, then you can know how far is it, or how far universe is expanding. So in other words, SOOS SOOS has own way to calibrate their supernova brightness, and once they know how far the supernova, they can estimate H naught. In another way, you have this supernova data where you don't know its expansion rate, neither you know what is the brightness of that particular supernova. So how you can do? You can use different data sets. For instance, in some data sets from the galaxies, which we call the cosmic chronometer data or the Hubble data, from where you know the expansion rate. If I know H naught, then I can easily compute what is the brightness of that particular supernova. Because we understand that the type Ia supernova has a similar kind of brightness no matter where we go, right? So something is constant there. Now there is a debate, and that is why this H naught tension is actually coming. But it is believed, there are different models they are working on, but it is believed that the supernova, whatever type of supernova we are using, or we are estimating this, they must have the similar kind of brightness. So this MB is going to be constant no matter where we go, no matter how far we are looking. All right, so once we have this constant, then if I know H naught from certain data, I can compute MB. So that's why we are clubbing together different data sets. Similarly, I can use the supernova data, and I can club it to Planck data. Now Planck data will give us different constraints. For instance, it can give you the constraint on H naught. It can give you the constraint on the densities of the components. So once I know H naught, then I can know the supernova brightness. So from there, by using the two different data sets, they will be calibrated. There is something called chi-square likelihood calculation. So they want to try, you have a model, they will vary your parameters, and from there they want to find out the probability for which you are going to get a best result. The probability of getting the best result has to be maximum, right? So they will vary your parameters in some particular ranges, and from there they will estimate, they will calculate they will calculate the probability. Once they are comparing the probabilities, they will find that okay, this is where the probability becomes maximum, and everything else, is minimum. So we can discard those things, and based on that, they are actually computing the estimation on the parameters, the free parameters, right? So this is what we are actually doing. So once we are here, there are all these important things are going here. Then we can use the execution file, or you can use the Polychord file. So once you are using the Polychord file, these are very important ones. You don't have to change it. I'm going to talk about maybe not in this video, maybe in different video. Here we have to use that how many data sets. Okay, how many data sets are there in one particular observations. For instance, if I use the Pantheon data, if I don't apply any filter, then there is I think 701. All right, 1701. In CC data we have 32 data sets, and similarly in the Planck we have 4 observables, so this becomes a 4. In DESI BAO it becomes 13. Similarly, we have to add all the data sets in order to compute the AIC, BIC, and all these things. Okay, so this is Polychord. Similarly, if I use the emcee sampler, then you can just use the emcee, and from here I am again calculating all the length of the data sets, and from here I have meant everything. And using this sampler, you can compute the constraint on your free parameters, right? So this is how the data analysis work. Now the part is that okay, these are the overall things that we are doing. Now the important part is that how we can write our model. What are we doing? How we understand this one? So let's move to our new screen. All right. In a standard GR, I hope you understand how this GR works. But as I have told you that my video, even if you are a graduate, a bachelor student, you can easily do it. So let's start from the basics, a little bit basics. So if I have my xn is always a dimensionless quantity. So in a natural unit, we are talking about just the mass dimension. So it has to be always mass dimension. So we are in a 4 dimension. Therefore, this becomes d4x, x in the length. Okay. And we have this square root of minus g. So what is the dimension of this one? Nothing. It's dimensionless quantity. All right. So x. Now x has dimension m to the power minus 1. How we know it? We can know from the uncertainty principle, delta x into delta, what is this? Momentum is equal to h bar. In natural units, h bar is equal to 1. What is momentum? Momentum is mass times velocity. Velocity is what? Velocity, let's say it is c. So in the natural unit, c is equal to 1. So this is also gone. All right, this is delta x. This is now 1. Delta p becomes m. So delta x is 1 over m. So this is mass inverse. So your distance over here I have written is the mass inverse. So mass inverse, now it has become m to the power minus 4. This is how, because whenever we are constructing models, we have to be very, very sure about the dimension of the models, right? Dimension of each and every variable that we're using. So now the Einstein's Hilbert equation, that is r over 2k square. Okay, so this is g is the metric, is the determinant of the metric. G is the determinant of g mu nu. Okay, now r is the Ricci scalar. Ricci scalar is derivative of this Christoffel symbols, so this becomes your m square. Okay, why m square? Because this becomes del by del x. And gamma, you already know that this is also del of mu of g mu. Now these are dimensionless parameters, so this d mu is basically d by dx. Again, this is your mass inverse, so it will go upside. This becomes m. So dimension of this thing is m. Again, there is a d by dx of gamma, so this will again become m. This is also become m. So this now is m squared. So r has dimension of m squared. Now this kappa, what is this kappa? Kappa is the Planck inverse, mass Planck inverse. All right. So once we are going to do it again, it has mass becomes square, m square. So this is m4. So here m4, here m minus 4, dimensionless. All right. So when we are trying to construct our model, we have to make sure that our xn stays dimensionless quantity. All right, it has to be always scalar. Right, it should not be take any dimensions. And this is how you can you write your scalars, because again everything becomes so easy when we write in terms of scalar. So all the indices must contract. Okay, so our xn always should be dimensionless scalar quantity. Now, what is this g mu nu? Okay. Oh, I have made a lot of mess over here. Let me just erase. I hope this is fine with you and so basic for many people, but bear with me. We are going to start the dynamic part very soon. Again, I have to multiply with the square root of minus g, and I can use the matter part. Now, in this matter part, I can contribute anything like g mu nu, that is minimally coupled. This scenario becomes a minimally coupled scenario where this Lagrangian of matter can contain our radiation. These are the components of a universe: radiation, baryons. We are talking about the protons, electrons, and all those things. They are electromagnetically charged. All right, and this is the dark matter. Why I'm differentiating dark matter and baryons? Because baryons are dust; they do not exert any pressure, but dark matter can exert pressure. You can know that if whether they are behaving like a baryons, you have to fit with the data. Or there are various other observations from where it was found that dark matter is also behaving like a dust, except that it is electromagnetically neutral, means that it does not emit any light, neither it absorb it. That's why we do not know anything about it electromagnetically, right? So it is electromagnetically neutral, and it just gravitate, means that it can change the path of the light, and that's why there are Einstein rings can happen. From that Einstein ring, they can estimate that okay, this galaxy contain how much dark matter, and from the behavior of the satellite galaxies or the few stars, people understand that dark matter is pressureless. Although there are many observations going on where we find that okay, maybe dark matter does not behave like dust. Maybe there are some little discrepancy, because again, many observations have shown that dark matter could be non-pressureless. All right. So we have radiation, there is baryon, there is dark matter, which is 25% of the universe, and then there is dark energy, which is again 69%, and something of 4% there is a baryon. So 25 and 4% is 29%, and rest is 71%. So it's near about 71 or something like that. All right. So 71, 68, 69, whatever you can take. All right. Now the fun part starts, that if I have to vary, okay, I was talking about that how we have to compute this Ricci curvature. We know that at the larger scale our universe is homogeneous and isotropic, and that is the best way to describe it, that how we can measure the lengths of two different points. Now if I assume that everything is homogeneous and isotropic, and inflation or many observations, I've already predicted that our universe is kind of flat means that the way you can see the screen, there is no curvature to it. So when curvature is zero, then it is called the flat universe, right? So for the flat universe, if I have 2 points, and I can easily measure their distances based on the coordinate theorem that you have already studied, but it's in the 4 dimension. And 4 dimension, I'm describing it minus dt squared plus a squared dx squared. Now a squared is actually but talking about the scales, right? In the universe, these 2 points, you can imagine that these 2 points are kind of stuck there, but the thing is that the space itself is expanding, right? So basically they are not moving here and there, the whole space is actually moving, so everything becoming big. So they are scaling up or scaling down. So before it was maybe here, but they are not moving, right? The space itself is moving. So initially it was here, again this is actually becoming. So how we can compare it? We can say that okay, there is something going on and it is actually scaling up. So why don't we, there is a distance between them. There is called physical distance. There is called co-moving distance. So physical distance is, let's say, 2 meters, right? But it is scaling up with, so this is called the co-moving distance. So here is the part of the scaling one. So dt squared and dx squared. Now in the, it is called the co-moving frame. We can use the co-moving frame that okay, everything is going in the direction with the expansion of our universe. So we are actually in the co-moving frame. Let's say that we are in the galaxy. So galaxy is actually going away from one point to another point co-moving, right? So we are in a co-moving frame. So everything else we are seeing just based from our relative perspective, and we are not actually we are canceling out every other type of local motion, that okay, whatever, if I am going here, are called, this is my local motion. So we have to, whenever we are capturing the data, we have to canceling these effects, and we are staying all the time in the co-moving distances, right? So this is how we have to deal with it. So minus dt square a is not depending on the spatial thing. It is just, well, depending on time, that okay, there is a cosmic time, and a is enlarging or decreasing, whatever it is happening. It is only function of this cosmic time. So ds square minus dt square dA square. Now here is not only x, because there are three spatial directions. So we have dy square, we have dz square. So a square dy square and a square dg square. So these are basically metrics. So what is we are doing is g mu nu dx mu dx nu, right? So tx, yz, they are certain coordinates of this point. What is going away and all the things, it's the a, right? Okay, then what is the g mu? G mu nu, we can write it in the matrix. This is basically the coefficient of dt is -1, everything else is 0. Yeah, right. And this is your a square and 0 0 0 0 a square. These are the components of this one. If you take the determinant, then you can just simply multiply everything, and this become like a to the power 6 with negative sign. So square root of minus g is going to be same positive once you are producting with negative sign. All right, so square root of minus g is your a cube. Now based on this, we can compute our Christopher symbols. From there I can compute my r, and then what we can do, we can just vary this action with respect to ds over delta g mu nu. It will give us our t mu nu. All right, and similarly it will also give us our g mu nu. So g mu nu is equal to kappa square t mu nu. Now g mu nu is the Einstein tensor, which is defined as minus g mu nu r is equal to kappa square t mu nu, right? Now it is dimensionally correct. This is you have to understand. So how we can say, I will write r00 minus g00 r is equal to, see, everything has to be contract. Whatever the indices you are using over here, it has to be same over here. Kappa square t00, right? So if I use this one, then this t00 is your, if I am not mistaken, it has to be rho, and then a square p, and a square p. So time component is becoming your energy density, and everything else is your a square, the pressure part, the spatial part becomes your pressure. All right, so r00 minus half g naught r, when you compute it, it will become 3h square is equal to kappa square rho. Now you will say that, okay, what is this h? H is how h is coming. So h is defined as a dot over a. A dot is basically dA over dt over a. Now you see that if you assume any dimension of a, it doesn't matter, because again it's a numerator, denominator cancel out. T is, I told you, again you can use your uncertainty principle. T becomes your m inverse. Now h your m. So h is dimension to be squared. Rho, you have to understand, energy density, it becomes m to the power 4, because energy density is your, let's say, mass energy density. So m becomes volume, right? So from here you will see that it becomes mass to the power 4, because volume is length cube, m to the power 4. Okay, m length to the power cube, and length is mass to the power negative, so mass negative, and then it will go upside, so rho becomes m4. Kappa is m to the power -1, it becomes m square. So this is now dimensionally correct. All right, so I have to use the metric. From the metric, I know the metric components. I can easily compute the determinant, and I know if I vary the action with respect to g mu nu, this is the very simplest thing you can do. G mu nu, I can get the energy moment tensor. In the left hand side, I can get the Einstein tensor, and the component wise I will get the independent equations. Additionally, this Einstein tensor, it is following the identity called Bianchi identity. So when you do the covariant derivative of this guy, then you will get that delta mu t mu nu is equal to 0. It means that in the homogeneous isotropic expanding universe, all the density will dilute away. there is no conservation principle. All right, there is no anything like, okay, we are using the conservation principle for energy, that okay, there is a amount of energy this one, then it when it will go out, then something will build up. Everything has to be constant, but not in terms of expanding universe. There is nothing like something constant. Okay, there is always, there is nothing like energy conservation principle over here. Here, this is our energy conservation rule. Just vaguely we have used. Delta mu T mu nu is equal to 0. So it will tell you when you will compute it that okay, you can have any energy density. It becomes d rho over dt plus, in this case, it becomes 3h rho plus p is equal to 0. What does it say? That whatever the energy density that you have, it will dilute away with the expansion of universe, because h is going to be always positive. Is how we have found out from observationally that h becomes greater than 0. It is a strictly increasing function. All right, if h becomes negative, then it shows that our universe is contracting, but the observation shows that h is strictly a increasing function. So d rho by dt, it's telling us that whatever the energy density we have in our universe, by the expansion of the universe, it is diluting away, right? So we have two equations, two independent equations, although we can have three equations, but one equation can be get by derivating, taking a derivative to another one. All right, so let's say that if I take a derivative, time derivative, and I am using this equation, continuity equation, then I will get Ricciardo equation or second Friedman equation, 2s dot plus 3h square is equal to minus kappa square p. Or if I just use this one, because I have g mu nu, I can use rij, gij, tij, then I will get this equation. All right, and then if I just use take a time derivative and use this equation, then I will end up over here. So although there are three equations, but one of the equations is actually becoming a constraint equation. So here, this guy over here, it's an algebraic equation, so we can use this as a constraint equation, that all the energy density must be equal to this Hubble parameter. All right, we will see very interesting things over here. Now, this rho is proportional to h square, okay, or h square is proportional to rho, all the energy densities that we have over here, all the pressures that we have, right, and all the energy density becoming dilute away. Now, what are the components that we have? We have certain components. Let's say we have dark energy. Dark energy generally shown by cosmological constant lambda. We have this dark matter. We have this baryon. We have this radiation. These are the major components that we by far we know. Right, now radiation captures many things like photons. There is a extra relativistic species, for instance, they are neutrons and so on. So I have made the code in such a way that it can capture everything. You can use neutrino and all these things. Now these are non-relativistic things, means that their velocity is very smaller compared to your photons. Here is the radiation. Now the physics for radiation is very well known, right, but the physics for these ones are less known. Okay, so when you use the class code, well, I don't have to go that one. All right, so we are actually working on background level, so we have to just understand how their energy densities are actually behaving. Okay, not in the perturbation level. So now let's say I am having these two components, baryon and dark matter. So I will write dark matter dot plus 3h p dark matter plus rho dark matter is equal to 0. Similarly, I can write rho lambda plus 3h rho lambda plus p lambda is equal to 0. All right. Now, for cosmological constant, p lambda becomes minus of rho lambda. This implies that your rho lambda dot is equal to 0. So rho lambda becomes your constant. This is your cosmological constant, which is filling our universe. Right. Uh, Now, similarly, I can say that, okay, PDM is equal to 0 of rho dm. And, this is when you are writing the pressure of any component becomes something called equation of state times rho. So equation of state is defined as the ratio of its pressure upon ratio of pressure to the energy density. All right. So omega for cosmological constant becomes -1. Omega for dark matter or baryon, it becomes 0. Omega for radiation is 1/3. This is the simplest one. All right, so we can also write the radiation rho dot 3h pr and rho r is equal to 0. So this becomes 3h. If you use p is equal to omega r into 1 by 3, so it will simply becomes your 1 by 3 plus 1 times rho r. 3 cancel out, it becomes 4 rho r dot plus 4h rho r is equal to 0. All right, so this is the standard equation for radiation. This is the standard equation for dark matter and baryon. This is the equation for cosmological constant. Let's say if you have another model for cosmological constant. Let's say I don't want to make my equation of state to -1. So my dark matter, dark energy equation of state could be omega 0. Let's say that it is not varying with time, but it is different than -1. So this is called one parameter extension of lambda CDM. There is another parameter, let's say omega 0 plus 1 minus a into omega a. All right, so what is this? This is called CPL parameterization. What we imply that your omega is depending on a. Now what is a? A is a scale factor, and we have normalized it in such a way that from the beginning of our universe, let's say beginning is around 0 and today is present. So present is a0 to which we have labeled it as 1. So from 0 to 1 everything is happening, right? So as your a becomes smaller and smaller, we are looking in the past of our universe, right? So let's say a is equal to, a can go from 0 to 1, right? So we can do the Taylor series expansion. Taylor series expansion says that okay, omega a is equal to 0, which we have talked about 0. Now we can say that okay, d omega over dA around a is equal to 0 and 1 minus a or a minus 1, because we are expanding around today. So everything is inbound 1 to 0. So this is my mathematical function, right? So once a becomes sinking, it becomes positive, and if omega a is your negative quantity, then overall this equation of state will become negative. How? Let's say that omega de is equal to let's say when we have measured it from the supernova data, maybe CC data, we found out that omega 0, which is a is equal to 0, right? And d omega by dA, which is another extension. Now it will survive when a is not equal to 1. Mind it, these are two constants, because d omega by dA, any value at a is equal to 0. It could be certain value because we are estimating the derivative with respect to a, and we are saying that okay, whatever the value at a is equal to 0. This quantity will survive when a is equal to not 1, means we are away from present. So let's say we use the Pantheon plus data and clubbing with the CC. So we found out that around present time it is near about minus 0.7. Omega A is, let's say, minus 2.9, right? So what will happen? Let's say we are going to calculate omega DE at A is equal to 1. Sorry, A is equal to 0.5. Now we are coming in the past. All right, so whatever the things that we can observe till now, we cannot observe what is happening going to be future. So future is kind of dark for us. We don't know what happened, so we have to extrapolate the behavior of any model, that okay, if the model is behaving correctly in the past, then this extrapolation might be correct, right? There is no way we can look for future things. So omega d a is equal to 0.5. What we will get? Minus 0.7. 1 minus a is 0.5, right? It's going to be stay always positive, and omega a coming out to minus 2.9. Now if I do this, then what is my computation says? My computation says is 1.45, right? So the overall thing, it's negative. The overall thing becomes 2.15, minus 2.15. So if you plot your omega DE with respect to A is 1 and we are going to 0, then it will coming out to be like, what do you say? Here it is 0. It's a y-axis. It's a negative x-axis. So let's shift it. So maybe this is your what you can say, minus 0.9, 0.7, and again it will come. So this will start, let's say here it is minus 1, here it is minus 2, here it is minus 3. So it will come like this, 2.15. So the way you are going past, the equation of a state will actually coming down from minus 0.7 to minus 2.15. That is called CPL parameterization of dark energy. CPL parameterization with two variables, omega 0 and omega a. Although these are constant, but these are your parameters, right? So based on the entire dynamics, it can take different values, right? So this is called dynamical dark energy, and that whether dark energy is actually a constant or differ from constant, we can find out by expanding its parameter. So in one parameter space, statistically, it is not significantly improved than LambdaCDM, but once we have uh, added additional degrees of freedom in terms of another parameter, we found out that the model is doing better than LambdaCDM. So with the recent release data from the DESI BAO or the Supernova, it shows that this model is more preferred. This model is just a mathematical model. It does not give you anything physically about the dark energy. It simply says that, the dark energy, what we think is not something that is having the negative pressure. The negative pressure is actually increasing when we look in the past, right? So the energy, and it's also dynamical because this is called phantom. Phantom line is that the greater the component that is having greater than -1, the pressure or equation of state, we are called non-phantom or accelerating regime. Once it is away from or lesser than -1, it becomes your phantom regime. So dark energy has now become phantom. All right. Now phantom has more problem because when we try to understand its effect, uh, uh, then we cannot express this type of tendency using our particle physics model, or we cannot say that okay, this could be anything particle physics model can comprehend the phantomness. Why? Because if you try to understand this behavior, then mass of any particle or the kinetic energy becomes negative. Now once this becomes negative, you can say that the mass becomes imaginary. Now this is not what we are familiar of. All the particles that we have detected in the LSC or something, it simply have the positive masses. It has the positive kinetic energy. Now what kind of this particle that has having a negative kinetic energy, imaginary kinetic energy? It's imaginary mass or negative kinetic energy. It's very complicated to explain such scenario, but we say that okay, this can be also explained, maybe dark energy and dark matter having some extra affairs, right? Extra interaction. Maybe your maybe our model that we are using, the Einstein gravity, that is Einstein-Hilbert action, it is not. It may be some function of FR gravity, or maybe some function of FG gravity. There are different models of gravity, modified gravity models. So this is not, you don't have to this is some kind of a apparent effect. This is not actual effect. So dark energy always may be negative -1, but because of this interaction, your effective equation of a state has now becoming like this. Now we are actually investigating that type of thing, that okay, what could be the dark energy, what kind of gravity that can mimic this type of behavior. This is the answer we are looking for. Now one thing, important thing is that this is one of the greatest problem. Another problem that we have is that although dark energy, although we are using this particular model, CPL model, but again when we are using the Planck data with supernova data, the H0 is more or less 67 to 68 kilometer. So although if we are invoking the phantomness, it does not elevate the tension between the Planck data and the source data we have when we estimate the supernova brightness. This result is around 73 kilometers, 73 to 74 kilometer per second per megaparsec, right? This is a huge difference. The huge difference is in terms of 5 sigma, more than 4.5 sigma. So this shows that you have a constant. H0 is your constant, right? It has to be same everywhere, but it is not same everywhere. The huge difference shows that there is something that we are missing. Although we are extending, although we say that dark energy is dynamical, which is very good. The dark energy is different from from LambdaCDM cosmology, but still it is not solving our problem. So this is one of the problem that we are facing since since 2 decades, and still we don't have any answer to dark matter, any answer to dark energy, right? So if you understand the model building and data analysis, maybe you can use your own model and you try to understand things in a different way, and maybe you will see that, okay, I can actually see where the problem is. If you will understand that where is the problem, then you can tackle these particular issues. That's why I have released my code, and code is made in such a way that everything you can see that, okay, this is where we are doing the tuning, this is where if I vary the parameters, then the result varies, this is how we are estimating things, that is the way we are thinking. So once you're familiar with the code, familiar with the data, then only you will able to look for the problem, that okay, this is the problem, this is how we have to think, and this could be one of the particular solution. All right. So now, how I have written the equation, that is the most important part. So inside the definition, and you have to structure it. Inside the definition, I have written equation. There is a time variable t, there is a variable that, okay, in this model how many variables are there, and there is a parameters. All right. So how I have organized everything? I told you that rho I any species dot plus 3h rho I plus pi is equal to 0. I have 3h square is equal to kappa square. Maybe I have radiation, maybe I have baryon, I have dark matter, plus I have cosmological constant or anything dark energy related. And another thing, I have 2h dot plus 3h square is equal to minus of kappa square. Pressure of radiation, pressure of baryon, pressure of dark matter, pressure comes from the cosmological constant or any other models, right? Now here you can see that there is a kappa, there is some kind of value, and I don't want to work in this dimensional quantity, because dimensional quantity are kind of having some scale. Make it a dimensionless quantity. How we can do it? There is a standard way to do it, but what I have done in a interesting way is that, okay, divide it everything by constant. 3h0 square is becoming kappa square rho r rho b rho dm rho lambda over 3h0 square. Now what is the advantage? H0 having the same quantity, so it is gone. So I've defined it that h over h not becoming smaller h is a dimensionless quantity. Now kappa square mass to the power minus 2. So, and this becomes the mass square, this becomes mass 4. Everything, if I just club it together, everything becomes dimensionless quantity. So for each species, I can write that, okay, kappa square rho r by 3h naught square becoming your omega r plus omega b plus omega dm plus omega lambda. So how these my omega r defined? Omega r defined is kappa square rho I by 3h0 square. Now at present, what they will becoming? At present h becomes your h naught. So this h your h over h naught. H, mind it, h is your time variable. All right, h depends on time. It's a variable, it's not a constant. Now when I am assuming that I am at a present moment, t is equal to 1 or a is equal to 1 or t is equal to now. At now, everything starts now. All right. So at now, h is your 1. Omega r will become omega r 0, omega b 0, omega dm 0, omega lambda 0. Now since it is a constant, it will remain constant. Okay, because kappa is 3h0 square, it's already constant, right? So these are the species that will play a very interesting role. Okay, so this is the definition of this dimensionless variable. This is called fractional energy density. Now this is a time dependent because rho I is your time dependent. But you can say that, okay, rho I is your time dependent. How do I know this rho I? Now here comes your continuity equation. So how we can write continuity equation? Let's solve it. So it becomes rho I dot is equal to 3h rho I with negative sign pi. Now what I will do is following d rho I will take h multiply over here dt minus 3. I'll use it, pi becomes omega into rho I. So it will simply become wi species and rho I, right? Now h dt, what it becomes as dt? Let me again write it. h into dt. H is your a dot over a and dt. Basically dA over dt into a into dt. Cancel. dA over a, which becomes d of log a. So as d of log a, we define usually by number of e-fold, d of n. It's similar to our time variable, but this n will actually go in the past. How? Because this is d log a and dn. A is equal to 1, it means we are in present. Log of 1 becomes 0, so n is equal to 0 because n proportional to log of a, right? N is your, this means n is your log of a, natural log of a. Similarly, as a becoming smaller, let's say we are in the past, a is becoming 10 to the minus 3. So what will happen? It will take some value, negative log of 10. Now it is not becoming 1 because log of base e. So it will have certain value, right? So minus 3 will be multiplied by this one. Similarly, a becomes your log of 10 to the power minus 7. So minus 7 into log of 10, right? So the more you will go, the more n will vary from n is equal to 0 to minus 8, minus 7, minus 6, minus 6, minus 7, minus 8, minus 16, and so on. Around minus 7 or minus 8, you have matter and radiation equality. Around n is equal to 0.3, minus 0.3, minus 0.5, you will have the dark matter and dark energy equality, right? So we have changed our scale from a 1 to 10 or minus 7 and things, or you can easily express it everything in terms of redshift. So a is becoming 1 plus 1 over 1 plus z. Now z becomes 0, is actually 1. Z is 3, 4, 5, 6, 7, 8, 9, 10. You are actually looking the universe in the past. Alright. And A will be smaller and smaller. So Z becomes 1 million, which is around the radiation epoch, matter and radiation equality. So your Z has to be 1 million. Then you can actually reach there. So computationally, if you express everything in terms of Z, then your system will go from 1, 2, 3, 4, 5, 6 to 1 million. I have to integrate something, or I have to find a solution around 10 to the power 10 redshift, which you cannot do it. So you have to use a different scaling. So I will express everything in terms of n. Why? It becomes very smaller. Again, I am not talking about something like minus 10 to minus 7 to minus 8 into minus 9. It's again a very difficult task to keep on going smaller and smaller. N serves me very well quantity. We are here 0, minus 16, and so on. I can always give some precision, and my integration or any solution would be extremely faster. So just using the method from the dynamic system stability, right, I can accelerate my code at an unprecedented level, right? So that is the precision. I'm gaining the precision, and I have accelerated my code. Okay, so everything I will express in terms of log of a. So I will find the solution d rho by dt in terms of dn. So d rho I by dn is equal to minus 3 rho I 1 plus omega I. This is the structure of our first order differential equation. What is my structure? My structure is d rho I over dn is equal to minus 3 rho I 1 plus omega I. Now you may say that, oh, I can just divide rho I and I will find the solution. I am not going to do it in that way. Why? Because why should I do it? Omega I is a constant, then you can do it. But what if omega I becomes, let's say, dark energy? Then it becomes omega 0 plus omega a into 1 minus a. Maybe it has some exponential function. Maybe it has 10 hyperbolic function. There are millions of, so far there are thousands of model people have already prepared with omega I. Right? This is called the parameterization of dark energy. Now you can parameterize it in a different way. Maybe you can say that, okay, our cold dark matter having a different parameterization. Let's say I can do the CPL parameterization to the cold dark matter. Then again, you don't want to do it because in some cases you are not able to solve it. So what is the best way? I am keeping it in a similar way, right? That is the interesting point. So what I'm going to do, Okay, I have already defined these guys. That all right. Omega I is equal to kappa square rho by 3h square. These are my variable. So I will write kappa square rho r by 3h naught square. I'll take a derivative of this one. First with respect to t, it becoming kappa square rho I dot by 3h naught square. All right. So what I'm going to do here, I will do certainly this equation, because d rho by dn. I will write over here kappa square, and if I just write here d rho by h into dt, 3h naught square, and I can write h over here, correct? So it will become d rho by dn. So d rho by dn is minus 3 rho I kappa square 1 plus wi over 3h naught square h. Now I have already defined this one. Rho I 3h naught square into kappa square. What is this? Omega I. So it simply becoming omega I 1 plus wi into h over here. And omega I, this is, you see, I have taken it with respect to dt. So d omega I over dt is equal to minus 3 into omega I 1 plus omega I into h. Now you can just simply replace it by r, by b, by e. So for radiation, baryon, dark matter, lambda, you have 4 different equations over here. Now I'll just take this guy over here. I am having d omega I over dn is equal to minus 3 omega I 1 plus wi. Now you may say that, okay, this is a beautiful equation, because omega I is part of the n and omega I is again a part of n. It could be a constant, it could be variable. I don't even care. I can simply plug it and numerically I will solve this differential equation. I don't need to do any effect, headache. I don't want to take any headache, right? So d omega by dn minus 3 omega I 1 plus omega I. And I don't have to talk about the scaling, that okay, what is the dimension is going to do, what are the dimension, how we have to, what is the value of kappa square and so on. Everything is gone, correct? So now when we solve this first order differential equation, how many initial conditions do we need? Just only one. Now since I am going backward in direction, when I try to solve this equation, d omega I over dn is equal to minus 3 into 1 plus omega I into omega I am actually integrating from n is equal to 0 to past to let's say minus infinity. So I am setting my initial condition omega I is n is equal to 0. So what will become? It becomes I comma 0. You see, now you can get the constraints. Now how will I get my constraint? Omega I0 I don't know. When I try to solve it, I have to specify what is the value of omega I0. What is the specific value of the radiation? What is the specific value of baryon, dark matter, dark energy? I don't know. What I will do, I will take this guy, I'll say omega lambda 0, omega radiation 0, omega baryon 0, omega dark matter 0. I will feed it to my sampler. I will say that I have certain data and these are my parameters. Fit it and try to find out that what is the probability by which I will get certain value for this one. Now mind it, when I'm writing everything over here, then at present I had something. I have a very beautiful equation at present. Where is it? Yeah, that is called the constraint equation. The Hubble equation is providing us a constraint equation. So 1 is equal to omega r0, omega b0, omega dm0, omega lambda 0. So let's say if I know 3 parameters, then I don't have to know for omega r0. Just I am subtracting it. Rest of the thing, I will get omega r0. But if somehow I know omega r0, then I can subtract. I can add this guy, this guy, this guy, and I will get a constraint for omega b0. Just 1 minus omega b0. So this is not a 4 parameter model. Due to the Friedman constraint, it now becomes a 3 parameter model. So I have a 3 unknown which I will find out from the data. Using this constraint, I will know what is the value of the other one. And what are these? These are becoming just initial condition for this differential equation. So my differential equation have been mapped like this. Now you may say that, oh, okay, Here you know how your densities will vary. You know these guys, right? From the data. Now, how will I know what is the H? Because if you see the lambda CDM, H becomes H0 into rho R plus rho M, whatever the components, right? Isn't it? So this is very interesting. 3h square or something like that. H is equal to h naught or something like that. So how will I do it? Well, I had an equation. One equation gives me constraint on one of the initial conditions. One equation is giving me this guy that how your density evaluation goes on. Another will give me, I had another equation, 2h dot plus 3h square is equal to minus kappa square p of total. So what I will do? I will do the following. I'll say that, okay, divide it like this. 2h dot by 3h square plus 1 minus kappa square p total over 3h square. Right? So 2h dot over 3h square is equal to minus 1 and minus kappa square p total. 3h square becomes what? Kappa square p total over kappa square rho total. That is the equation, Friedman equation. This is gone. P total over rho total is becomes what? Minus omega total. Or you know that what is your P total? You know certainly what is your rho total, right? But wait a second. Is everything okay over here? Yeah, we are dividing it. Yes. So now what I'm going to divide, what I'm going to do it minus 1 plus over here. Sorry, minus 1 plus omega total, right? So if everything is correct, yeah. So I can over here write minus 3 by 2 and kappa square, this has to be negative, sorry, this is also negative, and I'll take negative over here, 1 plus omega total h dot over h square. Now what I can get, this is one form of the equation, all right. Another form I can get, take it dh over h into dt is equal to minus 3 by 2 into 1 plus omega total. Now omega total is basically your p total by rho total, right? You don't have to worry too much. Now h dt becomes your dn. Dh over dn is equal to, there is h multiplication over here because h square over here, minus 3 by 2 h into 1 plus omega total. This is also a first order differential equation, isn't it? Now in order to solve it, you have to say that, okay, what is the value of h at n is equal to 0? It's becoming your h naught. So you will say that, oh, in addition to these parameters, I have another one. This is h naught. Just put it in the sampler and find the value from the data. So once it will go in the data, it will pick up some value and it will try to solve this one. And you will get a very nice curve of h. H with respect to n, whatever it is. And here it will take the h naught and boom, you will get the h evolution. Right. So once you know your Hubble, then you can know that what is at how far certain things are. And that is a very interesting thing that is called the luminosity distance. For the flat universe, we have the certain form of the luminosity distance, which is basically your dl. I have already explained it in terms of z, in terms of redshift, 0 to z, that okay, I'm in the present, go in the nearby redshift. Then you have this dz over h of z. This is this expression for flat universe. If you want to see that, okay, what is the curvature of the universe, you can adjust it. You can see the Carroll or any other textbook. From there you can easily find it. But you see that there is a integral involved over here. All the other equations having a differential form, h I am getting from differential form. Now you see that, okay, you can find the h and then again you can going to solve it. But problem is that, you know, in order to have our Planck data, I have to actually prove everything in the past. It is already written in terms of z. This is the headache. Why this is the headache? Because everything is estimated in terms of n, right? Now I told you that I have to convert it in terms of z, then I have to go in the million way. I will lose my precision, right? And the computation time will be enormous. And you see that for each and every z, because you know your data is like this, 0 0.01, 0 0.5, 0 0.3, maybe 0 0.025 and so on. So let's say that if you have 10,000 data, for each 10,000 data, it will try to calculate it. Although we can, make some interpolation, or we can say that, okay, there is a Z, right? 0 to Z. I know that what is the minimum and what is the maximum. And I will say that take some points, 9,000 points, and make a continuous curve. And I will just put it something, and it will easily give me the data. So this is a technical thing, okay? So you have to just know what is the minimum, what is the maximum, define it. But as I told you, that I have to use the Planck data, and for Planck data, I have to use the Z to the in terms of 10 to the power 7, right? And let's say that I from 10, let's say from Z is equal to 0 to 10 to the power 7, okay? I have to actually generate many million points, because 10 to the power 7, obviously I have to use 10 to the power 8 points. This is insane, isn't it? That, okay, it will, take my different Z and try to interpolate, try to estimate the continuous function. I don't want to do it. So how can I do? I will again use the differential form for this and replace Z by N. I have already done it in my different video, so I'm not going to do over here. There is a trick to do it. What you can simply do is, there is an integral, and derivative is the opposite of, or inverse of, the integral. So you may say that, okay, I can write dl by dz, right? You can use the chain rule, and you can say that, okay, this becomes 1 plus z square with negative sign, and there is, let's say, dz, right? And again, you have this integral dz over h of z, and again, you can do plus, and 1 by 1 plus z, you do the derivative of this one. So d by dz will act on this one, and because these are linear operators, so dz will be cancelled out, so this will become simply h of z. Now you know that now you have to convert it. How you can convert? N is equal to log of a and log of 1 by 1 plus z, and similarly you can just take it upper side, you will have minus of 1. So you can convert everything in terms of n. Now if you do it, then what we'll have, d by dl dn will becoming minus of dl negative of 1 by h. Now what is h? Over here, this becoming h over dh over dn. Now in this equation I have this. So how we have taken this guy? We have taken 1 is h over h0. So either, since h is over here, h is over here, both have the same power, either you divide it by h naught, you will get smaller h, or you can just simply say that because smaller h, you don't have to know also your h naught, so you will also free from here if you don't want to estimate, because there are certain data that cannot predict what is the value of h naught. So you just divide by h naught, you are free from this, and you can simply say that, okay, I know, I don't care about my h naught, I can know that h of 0 becomes 1. So this is becoming independent of h naught. All right, either you do this or you don't, it depends on you. So this will become simply your 1 by h into speed of light. There is one fault over here, you have to multiply with the speed of light in kilometer per second, and then you will get exponential minus of 2t. This is the differential form of luminosity distance for the flat universe. All right. Now one thing I can say that, okay, what I want to say that, okay, if you express this h in terms of h naught, let's say h over h naught becoming your h, so h I can write h times h naught. Okay, if you, let's say, you are you don't want to predict your h naught, then you know that for this integral, this is how you can express in terms of h naught. Now you can just take it over here, dl times h naught. So instead of dl, you can estimate your h naught into dl. Your dl is, your h naught is completely conform here. So you will have 1 by small h over here, you can just write small h over here. So when you write small h, you have to define what is your there is no need to define what is your h naught. If you use capital H, then you will estimating your dl, you have to define h. Okay, but when we do numerically, we don't know, unless this differential equation is going to tell us that whether you are evaluating this h, or you have evaluating this h. All right. So how our equation will look like? Our equation looks like this. What are the equations that we have? We have d omega I over dn minus 3 into omega I 1 plus omega I, all these species. Now dh over dn is equal to minus 3 over 2 into h 1 plus omega total, or whatever you can say. Similarly, I have this d over dln is equal to minus dl minus 1 by h, because this is the same thing. If you use this h, you have to write over here, times c, speed of light in kilometer per second, minus 2t. Now this t, sorry, t is not, this is n. Don't confuse it. Okay, so now this is your coupled differential equation. There are some independent equations. It could be maybe coupled differential equations. So everything is now in a differential form, and everything is estimated in terms of n. There is no redshift. So you don't have to solve any equation separately. All things can be simultaneously solved. Once it will solve this one, it knows the how this omega total can be got from here. It will get over here, and again once it knows that what is your h, it will take the initial condition over here. Now what is the initial condition for dl? Dl at z is equal to 0 remain 0. So it is actually going from 0 to 0 0.1, 0 0.0001, and so on and so forth. Right, at 0 it becomes simply 0. Right, and what are the observables that I have to define? Observables. So for if you use the cc data, there is your hz data at different redshift, and this is the h that you are estimating from the model. So how I can I can find it? I can just simply multiply by h. When you just put it in your solver, numerically you will get the array. Array means that there are a bunch of points from minimum to maximum. Now h0 you are estimating from your sampler. You can simply multiply it, because I want to constraint from here. I can easily figure out what is my h0. Then if you use cc, then there is a chi-square that you have to calculate. Chi-square says that okay, there is a h data minus h model. All right, h data means that this is your x data, x your redshift, and this is your y data. Certain things from observation, certain things from theoretical model, over sigma I square. And now you have to multiply with minus of half. Now this will give you the chi-square by chi-square for cc data. Now sigma is what? Whenever you have this data point and you have observation, then every data points have some uncertainty. This uncertainty is sigma. Okay, let's say for this data point this is 0.5, there is 1.5, then it will be squared, and once it will go upside, then it becomes a very bigger quantity. Okay, so if there are some samples where correlation matrix or covariance matrix is not provided, means that you have some bunch of data and these bunch of data are completely independent, then you have only diagonal element between these data points. There is no correlation, but there are always a correlation between these data points, because when you observe something from the telescope, there are a lot of errors that is coming from the telescope which are actually correlated. So the data points, these two data points are some correlation. All right, so now in that case you are having this correlation matrix sigma ij. For two data sets you are having 2 cross 2 matrix, this. So this guy and this guy will become your sigma I, because, and this will say that okay, how much these are correlated of diagonal elements, and this matrix is always a symmetric matrix. So for symmetric matrix you have to find the inverse of this symmetric matrix. So this becoming minus half, this is called the residue. All right, so I will take the residue. Now this is the square, so I will take 1 and then I will multiply with this sigma ij, inverse of covariance metric, and then there is a residue. By using this I can estimate the chi-square for another data sets. So this is the method how we can easily compute the chi-square for any data. Now again, for different samples, for instance the Pantheon samples, how we are computing the residue or something else, it's a little bit a complicated thing, right? Because there are certain ways to compute, that is called, this is called the likelihood. All right, there are different procedures to handle different data sets. So for the simplest one, this is the one we are following. For Pantheon plus, the things will differ. For Planck, this is the thing we are following. For BAO data, DESI BAO data, we are going to follow this one. But for Pantheon one, we are going to follow differently. And that is already given in the code. So now you understand that how we are modeling things and how we are estimating the Hubble as well as the luminosity distance. And there are many things we can, derive. Let's say that this is the luminosity distance. There is an angular distance, which is basically becoming dl by 1 plus z. So if I know what is dl, we can just divide by this one. We don't have to again derive this one again, right? There is no need. So once I know this one, I can simply get this guy. Again, it can be get in terms of n. But you may say that, okay, all the data set is actually given in terms of redshift, but we are taking everything in terms of n folds. How we can get this one? I can simply tell you that, okay, I know that n is equal to minus of log of 1 plus z. Now I know that where this n is spanning from 0 to certain value, like 0 to minus 16 or minus 17 or minus 20. So I know 1 plus z is equal to e to the power minus n. So z becomes e to the power minus n, right? E to the power minus n minus 1. So I know how this array is there. I will put the array, complete array. I will have the list of array, and length of this array is actually equal to length of this array. So all these solutions will have the same correspondence because all the solutions is actually estimated in terms of n. So I have this solution, I have this array. I will just simply map it. I will have all the answers with respect to z. I am not doing anything with respect to z. I am just computing everything in terms of n. I simply change the variable that you have already understood in class 11th and 12th, writing it and giving the correspondence that, okay, every point that you have computed with respect to n is basically your corresponding towards z, because I am just changing my x scale, which was previously estimated in terms of negative 0, minus 1, minus 2, minus 3, is will becoming now 0, 1, 2, 3, 4, 5, 6 million and trillion and so on and so forth, right? So this is how we have optimized our code, which is extremely fast. It will not take days, it will take few minutes. If you use the Pantheon data, it will take little bit more, 30 minutes, 40 minutes for LambdaCDM. If you use the Planck data, because Planck data involves a lot of integration. So in the whole code, what is important is that you have to express everything in terms of omegas of I. You have to be very careful how you are sampling your initial conditions, because you are constraining your omega i's for few things. Some and rest of the thing you can just use the Friedman equation. One parameter is another or solved, right? So lambda CDM is still 4-parameter model. Why? Because I can compute omega b0, omega dm0, omega lambda 0. I can easily know what is my omega r0. All right, estimate from this, and there is additional parameter that is called h naught. So if you use the another model that is called CPL with 2 parameter, then 4 plus 2, 6 parameter model. All right. So the more complicated models that you will use, your parameter space will increase. Understood? And this is from the data you can constrain these things. Now let's get back to our code, how we have planted everything in the code. And if you want to use your scalar field, or you want to use your another different model, or you may want to use the interaction, you just have to follow this similar procedure, and you can estimate everything from the code. All right. So what actually your data care about? Your data cares about your h. what is the function form of H, right? So where is my, where it has gone? All right, so this is this one, right? So d omega I will help you to estimate dh. Once dh is done, your estimate is dl. So these two things are the one that is going to be important for the data, to for the comparison and estimate the likelihood. Your data doesn't care about what are the things, right? But the way we have tricked things, we can estimate that okay, these are the initial conditions and we want to constrain these initial conditions, and these initial conditions actually giving us what are the content present in our universe, the physical meaning we can get from the data. This is how we are actually doing it, right? So let's go back to our data or our code and let's see that okay, what is actually happening. So first of all, we are in the equation T variable params, right? Now you see that I have a dark energy omega d, omega m for dark matter, omega b for baryon density, omega gamma for, let's say we have the photons. I have divided radiation in two components. One is there is a photon, and there is another things are neutrinos, right? Neutrinos are also relativistic particle, but they have the same equation of state, which is 1 by 3 times 1 by 3, okay, is equation of state. Another thing is neutrino, and another thing is that we are finding Hubble, it is small h, and there is dl into h0. Since we are finding h0, finding h over here small h, then we are actually calculating dl into h0. Now although I have written omega d can be anything, omega 0 plus omega a into, right, you can write a in terms of exponential of time, okay? So here time is not t, basically n, but for the sake of simplicity or some variable restriction, I have taken it t, okay? So now you have to understand one thing, that the order you have defined, you have to, when you are writing your equations, you have to also, basically here you are returning your variable, okay? So equation of d, equation of m, equation of b, all these things have to be same the way you have expressed your variable. Now what I have done over here, I have just defined what is my s dot over h squared. So this is my s dot over h square, okay? Now you know that from s dot by h square I can easily find out what is my small h. So this is your h, capital H over s dot square. All right, so this term will not have any change. Now this is just define my q parameter. This is called deceleration parameter, no problem. So this is just now definition. Now I have written equation of d, that is d omega d over dn. I have to write what is the right hand side. So right hand side of this one, whenever we write differential equation, first order differential equation, we have to only write the right hand side, okay? We do not write okay dx over dn plus y is equal to 0. No, dx over dn has to be right in terms of minus of y. That is the way we have to express our equations. Similarly, equation of m, I am taking it that dark matter is also pressureless, minus 3 into omega m, omega baryon minus 3 into omega baryon, omega gamma, gamma is minus 4 into omega gamma. Equation of neutrino is defined as minus 4 into nu. Equation of Hubble is h into dot of h, s dot, okay? H will multiply it. Now equation of dl is minus dl, whatever I have expressed. So now what this block will return means that when your time variable will come, this variable is there, the arrays, the parameters, what this block will give you, this block will give you actually the equation of dark energy, dark matter, baryon, photon, neutrino, Hubble parameter, and luminosity distance. Now once it is there, you can return variable. Now this one is very interesting. This one is actually when you try to solve your equations, let's say you want to solve it a very high redshift or n is equal to minus 20. In some cases, in some complicated models, the values, because these are again at every steps it is generating certain points, the value of points becoming infinity, or it can at some point it becomes 1 over 0. So Python will say that okay, it becomes infinity, or there is no value. So if it will detect anything such that there is no any numerical quantity, there are some discrepancy, because there are certain things where it get divided by 0, in that case you deduct it, and you return certain values. Now this value is very important. It will say that once we will evaluate it, if there is a such thing, it will measure the solution, and for this type of solution it will say that whatever the value that sampler has chosen for these parameters, it is bad and drop it from the analysis. All right, this is a very important stuff that I have given here, that for if your sampler, if your equations is not, cannot solve it for certain values of the parameters, then those solutions are unphysical solution and we don't want to carry out because it cannot be carried out, right? Now I have defined this block as an equation. All right, now I have to solve the numerical solution. So I say that OD, another block where I will just keep my parameters. Why I'm keeping the parameters? Because I had a solver somehow, somewhere, and it will simply giving us that, okay, these are the initial conditions, right? So all the initial conditions will come this place. So for me, my initial conditions are OD0, dark energy density, Hubble parameter constant, on OBH. OBH is omega B0 H square that I have shown already to you in the figure. Let me just show you again. Not this one, but Planck. This is your omega B0 H square. So omega B0 is the initial condition. H is H0 over 100. So this H is different than your that particular H. All right. This is your H0 over 100. And this value is over here. Since I have to use the Planck, I want to find out what is the constraint on omega BH. If you use only CC data or Hubble data does not provide you much sensitivity. It won't able to constrain omega BH. Alright, that's why we have to rely on the early universe data that can actually tells me that, okay, what is your baryon density. Now, for this current model, I am fixing N effective. N effective is basically your free relativistic species apart from the photons. Now, from the Planck paper, they have estimated it. It is like around 3.046. Now, if you want to change that physics, early universe physics, you may say that, okay, there is, there may be certain kind of coupling that exists between the photons, or maybe there is a dark matter and this neutrino that can change somehow, or maybe there is some interaction going on between these neutrino and the baryons, or let's say or photon, that can somehow change the structure. Because if you change that interaction, then your omega I or omega radiation is not going to be 1 by 3. It will be different from that. The equation will changes, and these will be visible at the level of perturbation, because from the perturbation you will going to estimate again how your CMB data or how your CMB temperature fluctuation will look like. Okay, and then it will compare and it will try to say that, okay, if you invoke certain kind of interaction between your photon and neutrino, or maybe neutrino and the dark matter, then things will be different. But if you don't do anything, then N effective is coming out to be 3.046. So assuming that there is a LambdaCDM, I don't want to go that way. I don't want to constrain the parameter. You can simply just do over here and constrain the parameter. Let us just fix it. So my parameter space is now shrunk from 4 to 3. Understood? Now I have defined double H as 0 over 100, and from there I can just calculate your omega H square. So this is omega H square is what? Omega gamma 0, that is photon density, into H square. H square is basically, this is H square, right? So from the Boltzmann equation, or the what do you call, the thermal stabilization, we have from the early universe, it is calculated what is the density independent to H. What is density? Omega GH square, and it is coming out to be 2.47, something like this. And we have already computed this TT from the CMB analysis. We are using it. So we are fixing this guy. We are also fixing omega gamma square, right? So neutrino and omega gamma is now fixed. You may keep omega GH as it is, and you may try to vary your N effective. So what you can simply vary, you can simply say that, okay, there could be, I have a doubt the relativistic species could be differ, whatever they have done, I don't care about it, I want to figure out by myself. Or maybe there is a dark matter and dark energy interaction that may affect the neutrino species. Then you can simply vary your n effective, right? So omega gh now is fixed. So the initial condition corresponding to your omega gh, this is your omega gh, omega gamma, is fixed from there. Omega neutrino, since n effective is already I'm providing it, I can easily constrain. The initial condition is already provided. So how I am finding the initial condition for the neutrino? OGH times 0 plus 0.227107 times n effective. Now the total radiation becomes this guy plus this guy. OGH plus ORH will becoming the omega radiation 0 into h square. All right. Now I have to compute, because these are two quantities like omega 0 h square. I have to find out this guy omega 0, because this is the initial condition, not h square initial condition. So I have to divide from this number. So OB0 becomes, I am constraining the OBH, which is omega BH square. I know the value, I can divide by HH, right? I will get the OB0. Just do the simple mathematics. Similarly, OR0, ORH I am computing, this is known, dividing by H0 over this one, I will get OR0. Similarly, OGH, OG0, I am getting it by dividing by HH square. Now, you see that I am not calculating the dark matter density because I am using the Friedmann equation. I know OD0, I know OB0, OR0, OG0. I am computing the dark matter density at present time. Now I have computed OM0, then I am computing OMH by multiplying by HH squared. Now then I want to compute it. What is the total matter? Matter means the dark matter plus dark energy into H square. Now this is important because this is important for our Planck data. So this is I have defined it DMH. Now I am saying that okay, omega 0 and omega are 0 because I am just using the computation from the Planck. But I have, if I use the equation over here and using the LambdaCDM, you see that there is no parameters. There is no parameter. There is no free parameter. Everything is already computed because dark matter, there is no free parameter over here, right? Understood? So, and all the other parameters will be initial conditions. So I cannot just give the initial condition over here because there is no need. The initial condition will be different, given in a different way. But there is no free parameter apart from those initial conditions, correct? But if you use the CPL model, then you will have omega 0, omega. These are the parameters. This is how you have to get the parameter. Understood? So that's why I have written over here params. Although for LambdaCDM there is no requirement of params, but still there. Once you switch off this guy, you can switch on this guy. You will always having params over here. Now you see that params is a array. Array means that it will have the values from initial to final, and they are labeled from 0, 1, 2, 3, 4, 5, 6. Now since I have two parameters, then I am using 0 and 1. So params of 0 will give you omega 0, params of 1 will give you omega 1, all right, or W1. So the positioning is very important. Therefore I have written over here that okay, whatever the param here, now the name should not be same. I am written over here params, everything. If I am using the params, this definition have to be use this name. But once I am out of the block, the position become important, name does not become important, all right? Now you have to also understand that once I'm outside this block, there is no role of ODOM. They become unknown for this one, all right? So whatever the variable that you have used will be unknown once you have out of this block, right? Now I am inside the block. You have to understand that whenever you name something, you have to name it uniquely. Do not use the same name for different variables. Now here we have param omega 0, omega in case I am using CPL. If I am using CPL, I will just simply comment it out and I will use this omega 0, omega 1 over here from here, omega 0 param, right? And I will say that okay, whatever the value you will get, you can just make an array, call it param. Now for the CMB likelihood, you have to given certain parameters combination. and it will compute when you will have these values like omega b0, omega m0, total matter density at present time, Hubble parameter, omega bh square, and dark matter omega mh square, omega dmh square, right? So these are the initial conditions that I have given, and there is a solution that I am actually finding it. Now this is the initial condition. Now initial condition has to be arrayed or positioning in such a way that how you have returning your variable. You cannot interchange any places. So what I am given that, okay, initial condition has to be OD0, OM0, OB0, OG0, OR0. Now 1 for the Hubble because I'm using a small h, and 0 for DL. Solution is solve IBPP, initial value problem. There is something called lambda. It is for variable, that is t, and y. You have to use this following thing, and you see that t is for the t that we are using, right? So if you just take your cursor over here, you will see that how your definition is there. This is the function that you have defined equation. Then first line is for t, which can take any array. Variable is just the variable that you are obtaining the solutions, and there is a parameters because I have defined the parameter if there is any. So I have used the name param, not params. So param is will take this array. The value of array is 0 0, but for LambdaCDM it does not take anything. Now I am going from present to past, 0 to minus 20, t initial, t final. So first block is always t initial, later one is t final. Yi is my initial conditions, and I am using that. Okay, I have to evaluate the solution at particular time time points. So I am dividing 0 to minus 20 in terms of t max. T max I am giving 9,000. 9,000 is meant it is dividing 0 to minus 20 scale in terms of 9,000 components. All right. So the more you will do, more it will be precise, right? Because I have to create a continuous function. Now it will first try to make your try to compute the points in those time stamps, right? And then I will have to use a approximation between these 2 points, right? It will try to take it. That is called interpolation. You may have heard in, if you have taken the numerical course in your bachelor's, then there is called interpolation. You know the function value at certain points, and now you want to create certain interpolating, that okay, what would be the continuous thing that is connecting these abstract points. So T max I have divided it because 9,000 is very huge number from 0 to minus 20. So it is giving me the more precise that we want. We should not use 1 lakh. It's a computation waste, right? So we have to be very discreet at, okay, how are we are, dividing these points. I am using the BDF. There is called backward differential backward derivative steps, and there is, I am dividing that, okay, the accuracy must be good, otherwise I am not going to get a good result. Then the accuracy has to be at 6 decimal places, and there is a tolerance, it has to be 3 decimal places. Now solution.t will give you the array of x-axis, and solution.y will give you all the solution for your variables like dark energy density, matter energy density, baryon, photon, neutrino. Here is your S solution and DLH0 solution. Now this will give you the N. Now I am projecting it in terms of Z, right? Just using this array over here, I will get another array. Understood? Now this will work when you use the return function, that if you get any kind of infinity, you just on it, and you can just on it over here. Now I have set those value in such a way that, whenever, because these are the increasing function, positive increasing function, distance can never be negative. Now I have used certain value for which the DLH0 will give you negative if they will get any discrepancy in the array. So once they will get the discrepancy, it will detect that, okay, there is a negative value. And once it will detect the negative value, it will simply say that, okay, the likelihood for that particular parameter is completely absurd. Just make that likelihood, make that probability to be extremely, extremely negligible. Then your sampler will again give you another value. All right. Now, since h is your small h, I have to multiply. I have named it hh. dl h0 is dl times h0. I have to divide it by h0 to get dl, the original dl. Now I will use the interpolation that is called the cubic interpolation, which is most important. That okay, I have the z is an increasing function, and I am taking the hs sol. That will give you the h value, that h of z at different redshift. Here it is basically giving you the continuous function, and for the continuous function I can just give you that okay, what is the value of h at 0.1. It will simply give me that particular value. Similarly, I am interpolating using the cubic spline zz times zz and dl sol, right? Here I am computing the chi-square for Hubble value, Hubble data. What I have given is that h val is actually your theoretical value as well over here, and there is a s data, which is the part of your cc data, right? So maybe I don't have data over here, but if you just see, this guy is your zz. Okay, this is the redshift, and this is the corresponding value. So your x-axis, your y-axis. So what is basically happening is that I am finding the value of Hubble, the theoretical Hubble, at every redshift that is obtained from observation, right? And comparing it, the value, with the y observation, and taking the subtraction, that is called the residue. You understand a point? That I have the Hubble function, and I want to know that what is this theory is actually predicting the value of Hubble at each distinct redshift that has been obtained from the observation. Once I have that value, I will compare directly with the observation value. Now this is the array. This is also an array. Whatever you will get is the array of one dimension. Now I have the chi Hubble. Then chi Hubble becomes minus 0.5. This is the residue of Hubble in the transpose. This is the covariance matrix, and again this is the uh, Hubble data, right? So this is the 1 times the matrix form become the row. Let us say there is a 17 Hubble data, or 32 double Hubble data, 32 times 1. Here this becomes 32 into 32, and this becomes 1 into 32. So everything will returning the one scalar, because chi square is just a one value. It cannot be an array. If you get any error, maybe your product is not same. So you have to understand the dimensionality of your matrix. Now I have not explained the Planck data, since this video is again out of scope. I will later explain you this the Planck, then what is the sound horizon and all these things. But for this moment, you have to understand that okay, once you have found out what is your DL, all right, what is your Hubble, then you just have to use everything, because your work is done. You have to invoke your model in the equation the way I have described you. Once you have to solve it using the param, and everything has to be correct, given you initial conditions. Once you are done, then you can just how your h-val dl-val is done. So this is the major thing that you require. All the other things will automatically take these names. They know what are these ones, and it will automatically calculate everything. Like the for supernova, it will take your dl val over here. All the array it will take. All redshift is corresponding to the observation redshift. It will automatically compute your dl val from the model at every redshift. It will compare it, and it will find your residue. Now this is a little bit wrong. I will make it correct. This is the one you have to use for Pantheon data. If you want to use the non-SUS calibrated MB, right? So for here you have the DLVL, you have the redshift, and another one is redshift helicity. That is actually corresponding to two. There is a two different redshift. There is called ZCMB and there is Z helicity. So these redshift have to be corrected. All right. So this correction has to be I told you that computing the likelihood is differ for different observations. So this is not in your theoretical ones, but it is coming from the observation one. So you have to go through the paper and you have to say that okay, what they have used, right? So I have given the paper name and all these things. From here I am computing the mu val. So there is a distance modulus. The formula is 5 into log of 10, and there is a DL well. Okay. So this is written in terms of dA. This is not written in terms of uh, luminosity distance. If you see the textbook, you will see that 5 into log 10 into DL. Okay, there is no dA, but this is converted into dA. And there are two redshift that has been used. There is redshift and redshift helicity. Both the formula is basically same, but we have to use these corrections in order to get a correct mu value, and then 25. So this is the same thing we have to use over here also. So you have to use DLVL over 1 by over 1 plus redshift. All right. So once I have taken it, I have computing dA, and then I have to multiply over here 1 plus redshift times 1 plus redshift L, and then multiply it. I have to use wait a second, I am going to use this guy over here, this over here. You see that there is an error, you can see, because it is not undefined. So you have to define that. Okay, so now I have changed it, and you have to make it square, right? So this is how we are converting everything, and we are using, because we are multiplying it by two things. DLVL by one redshift will actually give you the DA, but since I am multiplying by another redshift over here due to corrections, then I have to divide it so that everything looks same, remains same. Now there is a mu of Vn I have computed, and there is a mu, but I am using the MB, small MB, apparent magnitude of brightness. Two things I am subtracting. Now I have to, if you see one of my paper, then you will see that there are additional absolute brightness that is coming from if you use this particular column, right? So in many scenario, they are actually constraining this MB, but you don't need to constrain MB, right? I will explain it in my later video what is actually going on. So you don't have to actually understand this part. What we are actually doing is we are marginalizing it, this MB, because again we have to use some other external sources in order to get this capital MB. Capital MB is your absolute magnitude of the brightness of supernova. Now since we are having this one from the data, then why should I compute the same thing from the model? Because these two things will automatically get cancelled out. So there is a way to actually marginalizing this capital MB, and you can find it just by following this paper. All right, this is one of my paper, and you will easily get it. You don't have to do anything. You don't have to learn everything. It is just a technical aspect. Similarly, you just have to invoke your DLVL as well, and there is a RD. RD will be automatically calculated over there. Similarly, for Planck, you have to just give your DLVL as well. There is a CMB params, I have already defined it. There is RSVL, it will automatically compute. And similarly, there is ZS, it will be automatically computed. So once these are computed, you don't have to. So once you have given your model and you have found out, extracted the arrays for luminosity distance and the Hubble function, everything else will be computed automatically. So now I have defined as a log probe whatever the chi total over here, whatever the ODE is giving you, what this chi total. So I have taken this one and made another block called the log probe. I am saying that okay, whatever the value, because it will return just only one value. No matter how many data you are using, it will simply giving the sum of all this chi total. If I am using chi Planck, chi DESI BAO, I have to make sure uncomment it. If I using CC data, I have to use chi CN. All right. So you may see over here chi Hubble. I have to write chi Hubble over here. Then it will be simply algebraic sum of this chi total. All right. So I will write chi Hubble. That will give me chi total. I have made another block. In another block, I am just using the result from this ODE solver. Now this is the params. Still, where is the param? Right? So log probe has the information of params, it will go to, once it will give you the param, it will compute everything. From there it will give you result. So once things like parameters will go over here, your ODE becomes activate. Once ODE becomes activate, it will go to your differential solver so that your equation becomes activate, and it is actually going in the backward direction. All right, so your sampler will sample, this data points will, parameters will come, and then everything will activate. So result will be over here and it will return in result. Now let's say that, okay, I'm using the Polychord. So Polychord I am using, what is the file name? BAO LCDM equation. So I'm importing BAO LCDM. Where is my BAO LCDM? Yes, BAO LCDM equation. Now for this BAO LCDM equation, what is the, which block I have to use? I don't have to use the ODE block. I have to use this block because this block is doing everything, because this block is containing my ODE. From there it will actually giving us my chi total. So over here I have defined something called likelihood. This is the likelihood estimation, basically the same thing, right? This is my parameters. Now I have named it that, okay, first parameter is OD0, another parameter is H0. Make the parameter list in a form of array. From the BAO lambda CDM equation, bring me, oh gosh, bring me the log probability, and I will simply insert these params. So now I have defined my theta, that is called standard things, that this is the parameters that I want to constrain from the data. Make it an array, invoke it from the lambda CDM equation. I have this log probe giving this one, but now this block does not know what is your theta, how it will know the value. Then I have to define a prior, what is the range of these guys. So it will make actually your polychord is making a hypercube of n dimensions. So theta, everything it will make it will expand your cube from theta np zeros of length of hypercube. So it will just simply make different vertices, that what is the length, what is the dimension of the cube. So the dimension means that, okay, how many parameters are there. So I have a parameter, so I am defining certain things, that is called theta. This theta will take the array, right? That's why it is called np of 0. So theta of 0 will uh, give me the uniform range of dark energy density from 0.1 to 1. So from 0.1 to 1, it can initiate any type of value, any random value. Similarly, 30 to 100, it will initiate the value for h0, because we know that h0 is around 67. So 30 and 100, we are not giving us any biases. So it can take any value. Similarly, OBH will depend in the range of 0.02 to 36, right? So it can become simply like 0 to 0.1, because 0.1 is the very higher than 0.022, right? So this becomes theta 2. So this is the hypercube of three parameter space. AIC block is there. So now there is no derived parameters here. There is a live points. I have to initiate that. Okay, how many live points or how many workers are there, that will actually generate this one. I will define the name. What are the name of the parameters? What are the labels we are going to use in terms of latex? And there is a n dimension. N dimension will depend on the name. So you have to change the name. If your model will change, it will automatically calculate that what is the length of your hypercube. So n dimension is there, right? There is nothing there. You have to follow the polychord, that if you want to do the parallelization, you have to make it true. It will do the clustering, right? So polychord is already inbuilt with the something called multiprocessing, right? So if you have different CPU, if you do not use the multiprocessing, it will not going to do anything, right? So for polychord to use the multiprocessing, you have to use the MPI4PY. So I have already given that how you have to run it. So you have to define a dumper. It will collect all the dumps. So here the polychord will run. Polychord is run. Polychord, from the polychord block, you have to run polychord. So this pi polychord is coming from this import polychord, which you have to install in the Python. All right. So from this pi polychord, it will run take the run polychord. From here it will just give you the likelihood. First of all, it will go to likelihood, Here there is a theta, and from the theta it will take the n dimension. There is n derived is already 0. Settings are there. What are the settings you have done? And prior range, the prior range that we have already given. This is the definition of prior. It will give you all the values, right? So prior will automatically take this n dimension, and likelihood will automatically take all the prior. Dumper is equal to dumper. It will take all these things. So once it will take, Polychord will do the work. You don't have to do anything. Once everything is done, it will come to rank 0 and it will give me the plot of this one, right? So in order to run your Polychord, you have to open a terminal. You have to write mpi run dash np. You have to define how many CPU cores you have. If you have 6 CPU or 11 CPU, whatever it is, do not exceed it. MPI run, it will take automatically 11, and then I have to write that, okay, if you have Python 3, make sure that which version you are using, what is the name of the Python. So Python dash u, then you have to see that what is the name of your file. This is my Polychord underscore execution.py. So you have to write the file name and then hit the enter. So you can use this command in any terminal. It may be your Linux, or maybe your Windows, or maybe your Apple. Just hit this one, wait for it. It will print everything, and once everything is right, you will get the result. If you change this one, let us say it is 1, then it will just use your 1 CPU. It will, if you use the 10, it will use these 10 CPU. Automatically parallelization will take place. You don't have to do anything. Make sure that you have already installed MPI4PY. all right. If you use the supercluster or high performance computing that maybe your machine should have, then you have to make certain bash file. I will update it in my later video where I will talk about these Planck and all these things. So I hope if you have I hope you understood all the part, because the video has already exceeded 1 hour. So it's very exhausting, and to summarize everything in a one video is a very difficult task for me, but yeah, that's fine. And this is how you have to start it. So just invoke your model, incorporate your model in a definition, and then you are done. You have to make sure that how your params are there, and you have to also modify this guy likelihood, and you have to also modify this one. Once you have modified it, everything is done. All right. So I hope you have enjoyed this video. Maybe it will be so much painful, but obviously you are a research guy, then you have to go through this pain. All right, because in order to learn something, you have to give your time, right? Okay, so if you enjoy it, make sure to hit your comment, hit the like button, subscribe button, and comment whatever the query you have. Or later on, I will bring more videos, and I will also make sure that I will make more videos on the analyzing the research papers, right? For long I have left it out, but now I will start to analyze other research, and I will discuss what are the problems with that paper and what are the ideas, how they have done it, and so on. So this is Sudham Cap signing out.